Observational fact number 2. If a charged particle is moving through moving perpendicular through an already existing magnetic field, then it experiences a magnetic force that is perpendicular to both velocity and magnetic field. So, if you have a horseshoe magnet, it has magnetic field going out of north into south. This is our already existing magnetic field. With a variable b. Okay. Now, what we're going to do is we're going to take a positively charged proton and we're going to shoot it through the uprights. Trying to shoot it like kick a field goal. Get with that? Bless you. So, we have a positively charged particle. Velocity is coming out of the board. So here we have a moving charged particle that is moving perpendicular to the magnetic field. And therefore, it's going to experience magnetic force. Which way this is going to be forced is completely unintuitive. Okay? And this is where our right-hand rule number 2 comes in. Okay? So, right-hand rule number 1, what we learned yesterday. Okay? Magnetic, what do your fingers represent? Magnetic field. In right-hand rule number 2, your fingers aren't curled, they're flat, but your fingers are still the magnetic field. Okay? In right-hand rule number 1, what does the thumb represent? Current. When you're dealing with a wire, your thumb still represents current. But if you're dealing with a single charged particle, it just represents the velocity. It's which way things are moving. You okay with that? Okay. The addition is when you deal with a force, when something's experiencing a force, that tells you I need to have a second right-hand rule. Okay. Get your hand flat, not curled. Okay. Because your palm exerts a force. You would never want to exert a force with your fingers curled. You break your fingers. Get it flat when you're exerting a force. Okay. Your palm is what pushes. Okay. So when you're doing this, everybody get your right hand out. Okay. What part of your hand corresponds with the magnetic field? Fingers. So lock your fingers to the right. The magnetic field is going to the right. So stick your fingers that way. Okay. You're going to commit your fingers to that. You're going to lock them in the vernacular of IED. You are going to constrain, like if you took the engineering classes, you're going to constrain that. Okay. So your fingers are always going to the right in this example. Okay. You can pivot it anyway. But if you don't do that and you're like trying to find something else, like, well, the thumb's going to, you just lost ground. Okay. So lock it in there and then pivot. What part of your hand corresponds with velocity? Thumb. So your thumb is going to be directed which way? Circle the dot. You're looking at the arrowhead coming at you, like, duck. Your thumb's coming out of the board. So which way is your palm pushing? Up. This thing is going to be forced up, perpendicular to both the velocity and the magnetic field.
So I got a question about the quiz last night.
Yeah.
There was one that had like sine, cosine on there.
Oh, did I not delete that?
I like looked that up.
I tried, yeah,
But
it had
good
sine
thing
and
the quiz was
cosine,
10
and
minutes.
I remember perpendicular, but I do not remember sine or cosine. Being in the
I apologize. I thought I deleted that one. Did it not? That stinks. I spent some time on that. Did you guys have questions or like what part, like what does your thumb represent?
There was one about like your hand.
I got a 3. It's just that one. I chose cosine instead of sine.
Yeah, I thought I deleted that. I apologize. Obviously, I didn't.
I was wondering when that was going to come into play.
Yep. Well, interesting. Okay. Man.
So does it or does it not?
Did it come in play?
Yeah, like will we learn that?
Sort of. I'm taking a different approach this year. So yes and no. Sort of. Okay. Now, why this happens, I've got a sort of a good answer, sort of not. So foundational fact number 1 says moving charged particles create a magnetic field. The fact that this is moving, it creates its own magnetic field. Okay? Those two magnetic fields, the blue one, you're welcome. Remember your worksheet.
Yeah, I will.
The blue one and the magnetic field created by this guy interact and cause this force. You okay with that? Now, why it goes up, this part, I think if you talk to other physics people, they were like, but this is my best guess. So this guy's creating its own, the green's creating its own magnetic field going this way. First right hand rule. It's going the opposite direction of this, so it's attracting. It's going the same direction as that, so it's repelling. You don't need to know that. That's just for the people who are like, why? Because I'm that type of person too. Like, that's why? That's so dumb. Okay? It goes up. Good? Now, the exception is if this is negatively charged. If it is negatively charged, then you are going to push not with your palm, but with the back of the hand. Okay? The way I remember that is palm pushes positive. When you get backhanded, that's a negative connotation. Okay? So negative, use the back of the hand. Okay? Good with that? So if it was negative, you're still going to be using, your fingers are still going to the right, your thumb's still going out. You just be pushing it, not with the palm, but with the back of the hand, and it'll be forced down. Good with that? Okay. Today's pretty much is devoted for you getting ownership of the right hand rule. Okay. So Here we go. Okay. What part of your hand corresponds with magnetic field? Fingers. So your fingers go up. So lock them in there. Okay. What part of your hand goes with V? Thumb. So which way does your thumb go? Comes out of the board. You're looking at the arrowhead. Better duck. Okay. Which way is this being forced? Being pushed positive palm to the left. Correct. Yep. Yep. If it was negatively charged, you'd be pushing with the back of the hand, so it'd be going to the right. Okay. Yep. You could. All right. Next question. Circle with an X means what? Into the page. So what do you do with this information? Fingers go into the board. Into the board. Okay. What do you do with this information? Thumb goes to the right. So you keep your fingers going in and your thumb goes to the right. Okay. Watch this. Back of the hand is negatively charged. Down is the correct answer. If it was positively charged, your hand would still be held the same way and be forced up. Good with that? Okay. Now, I can give you 2 out of the 3 things. So far, I've just been giving you magnetic field, velocity, find the force. If I give you any combination, there's always 3. Force, field, and velocity. I can give you any 2 of those combinations. Combinations of any of those 2, and you have to find the third. So in this example, I gave you the force and the velocity. I want you to find the direction of the field.
FB is your palm. B is going in. B is where your thought is. Because so B is putting back this.
Okay, here we go. This tells you to do what? Thumb goes into the board, into the page. Okay? So you're locking your thumb. Okay? What does this go with? Palm, because it's positively charged. So you rotate it until your palm is facing to the left. And you're looking for fingers. Fingers are going down. C. Good with that? Okay. Next question. Okay, it's a trick question. See this right here? Correct answer is E, but what is the right answer? E is the right answer, but what actually is the answer? If it's not none of these, what is it?
Wait, you said if it's not none of these, it's not E?
No. It is none of these. E is the choice that's given. So if this is a free response, yeah. If this is a free response, what would the Y0? It needs to be moving in order for it to exert a force. A charged particle does not interact with a magnet unless it's moving.
It's moving the opposite way.
It's just sitting there. If it, in order for it to exert a force, it would have to be moving perpendicular to the magnetic field. But it's not. Next question.
Say it back.
Okay. What do you say? Show your neighbor. Show your neighbor with your right hand. Show your neighbor. Your fingers go which way? Out of the board. Okay. What part of your hand goes with this? Back of the hand. So keep your fingers locked this way. So I'm just rotating this. Back of the hand goes down. Your thumb is what you're looking for. Thumb's going to the left. Okay. D. Good with that? Next question. It's going to the right.
Smiley, which way is the velocity going? Going in,
To the right. To the right. To the right. Okay. This is another trick question. Do you remember this equation from the video? Specifically, that the velocity needs to be, there needs to be some component, some part of velocity that is perpendicular to the magnetic field. If the velocity is parallel to the magnetic field, no force. Get with that? There has to be some component of velocity that is perpendicular to the magnetic field. Okay? All right, so magnetic force is equal to magnetic field times the charge times the velocity perpendicular. So what are we going to have to do? Use vectors and find the components. Oh, buddy. Okay, those in pre-cal, we need to switch back to degrees from radians. Okay, you need to draw your triangle again. Okay, it's the first time we've done this semester. Yeah, we haven't done this in a while. Not kidding. Now, instead of doing x and y components, I'm going to write it this way. V parallel and V perpendicular. Because this could be going anyway. Not necessarily x or y. I drew it in this case, it'd be x and y. But it could go anyway. So I'm going to say V parallel, V perpendicular. I know this side is 2,000 meters a second from the problem. Okay. Tell your neighbor what are you going to use to find V perpendicular? Sine, cosine, tangent, Pythagorean theorem, what?
I would use sine.
Okay. Now, those who did answer, I heard sign, which isn't surprising that they're going to be the ones answering, but check this out. This is the next level. Okay, I'm bringing 2000 over here. The way a lot of textbooks do this is this. So your magnetic field, 6.5 Tesla. Your charge is 33 microcoulombs. Again, drop the positive negative sign on the charge just like normal. So I got 33 times 10 to the negative 6 coulombs, and you convert that to coulombs just like microcoulombs. Okay, and then for V perpendicular, what they do is they just go straight away 2,000 meters per second sine 40. Multiply all that together, and you get 0.28 newtons. Get to that? Questions there? Okay. Follow-up question. We found this to be the magnitude of the force, how strong the force is, but which way is it going to be forced? What is the direction of the force? To answer this question correctly, listen to this. Ready? Do not stick your thumb in the direction of the red arrow. Do not stick your thumb in the direction of the red arrow. Stick your thumb in the direction of the perpendicular component of velocity. Does that make sense? Do not stick your thumb in the direction of the red arrow, which way I just care about the perpendicular component. Okay? So your hand should look like this. Okay? So which way is it being forced? Into the board. Probably a lot more comfortable like that. If you find yourself about to break your wrist, there's probably a different way to do it. Okay? I haven't had anybody break the wrist yet. Well, so what I'm saying is, nothing that you go through, you're gonna have to break your wrist. Okay? Good with that? All right. So, when am I ever gonna see this? Why? Who cares? Or maybe just prove it. Like, it might be a better first step. Okay, so, need a video. Back here, you can stay in your seats.
Uranium.
That?
Yeah.
I don't know, some kind of gas. Yeah, a little bit.
Make like a reactor with it or something.
Yeah. If you just sat there long enough, yeah.
Why didn't you say that?
All right, so this this is cathode. This is a cathode ray tube. It shoots electrons this way. Okay. Okay. So in here, there's a certain gas that as electrons are going through, it excites the gas and it illuminates. Okay, so you can see the path the electrons are going. If you sat here and like just for like a long time, yeah, that wouldn't be healthy. Okay, this guy right here is a pretty strong magnet. It's called a cow magnet. Okay, the reason why it's called a cow magnet, kind of looks like a pill. Cow. Moo. Okay, cows aren't the smartest critters in the world, and so they occasionally will eat some barbed wire, which should be a little wreak some havoc on the digestional tract. So what they do is they stick one of these down, like it swallows like a pill, and just sits in the cow's first stomach and collects any, miscellaneous barbed wire that they might have eaten, and just stays there. And then when they butcher it, pull it out, clean it off, and put it in another cow. Okay, so it's a pretty strong magnet. Okay, so this is the North Pole. This is the South Pole. Magnetic field goes out of north into south. Okay. What I'm going to do is I'm going to stand here behind this. So the field's going out of north into south. The electrons are being shot this way. So I want you to hypothesize which way the electrons are going to be forced when I come up here with the magnet behind it. This is the North Pole, so the magnetic field is coming this way. The electrons are being shot this way. Electrons are being shot this way. The magnetic field's going this way. Which way is this going to be forced? Everybody have a hypothesis? Here we go. Were you right? Yep. What would happen if I flip the magnet around? So the magnetic field now is going this way, out of north into south. Which way is it going to go? Ready? Were you right? Okay. Now, this is a cool demonstration. Like, yeah, okay, proof of concept. It did what we thought it was going to do. What about how does that apply to life? So, if you ever, these old school TVs are known as CRT TVs. CRT stands for cathode ray tube. So these box TVs, your grandparents might still have. Okay, they're beasts to move. They're really heavy. But inside here is a cathode ray tube. A really sophisticated cathode ray tube, because the way it makes pictures is it shoots electrons out of an electron gun, and through the magnetic field steers the electrons up to the screen, and then it goes next line, but it does this so fast, like a flip book, that it looks like a continual motion. Okay, so the engineering to go behind that's pretty incredible. To be able to steer electrons going. If you've ever seen old movies of like TV screens in the camera, like there's a bar that goes down. That's the offset between the frame rate of the film and how quickly the cathode ray tube is shooting electrons. Okay. Now, you might have heard the advice never bring a magnet near a screen. That came from these cathode ray tube TVs. Okay, because the way they steer the electrons is through a magnetic field. That was a familiar sound growing up. My dad was like, someone's watching TV. Okay, wait for it. Oh yeah, that's good stuff right there. That's high quality. Okay, now it uses a magnetic field to steer the electrons. So if you take a magnet and you place it near it, it messes with the path of the electrons. Okay, and so like what would happen is someone might have placed something magnetic on the TV, like a tool or something that happened to be magnetic, and they turn on the TV and like, oh no, and then they take it away, and then it's like permanently discolored. Some of the higher quality TVs had a degauss function that could like reset the magnetic field. But if you didn't have that, your TV was like, okay, but you can kind of like brush it, like kind of figure it out. That, like if you do too much, it's like crazy. But then it's like, oh dear, and you kind of like pretty good. So there's chances of like, no, Dad's gonna kill me. Like I can figure it out. Okay, we're good, we're good. Okay, good with that. There you go. Okay. Yeah, that's normal. All right, so give that one a shot. Tell your neighbor. Show your neighbor. Show your neighbor. Right hand. Okay, this little thing right there is showing you that's just a vector. That's how you label a vector in a textbook. The direction of the magnetic field is the x, like a circle with an x. Show your neighbor. They're electrons. Here's your hand. Going into the page, fingers to the right thumb. They're negatively charged. Down. Okay. All right. So show me the direction that this guy is going to be forced. Correct answer is up. Okay. So now, if this was free to move, it wouldn't immediately just go up, straight up. It's moving. It has inertia. Okay. So it's going to do something like this. It's going to be moving now that way. Does that make sense? Okay. Which way is it going to be forced now? It's moving this way. Which way is it going to be forced? Show me. Fingers are still going in. Thumb's going this way now. It's going to be forced. Okay. Perpendicular to the velocity. Okay. Over time, this is now going to go that way. Which way is it going to be forced? To the left. And it's going to go, let's pretend there's a lot of magnetic field here. Which way is this going to be forced? As time goes on, and this magnetic field, let's say it was all over the place, how's this going to move? In a circle. You see that? How the magnetic field's always acting towards the center. So we could say in this scenario, the magnetic force is playing the role of what? Centripetal force. Okay, I could make you do the math with this, but I'm not going to. Okay, but know that that's a thing in college, like straight up, just like boom, they're like, hey, look at this, kids. Okay, so it's always acting perpendicular to the way it's moving, always acting towards the center of the circle, playing the role of centripetal force. Okay, so if you have a moving charged particle going in a magnetic field, it's going to go in a circular path. Okay, here's just an animation of this. It's going in a spiral because it gave it a little bit of velocity going this way, parallel to the magnetic field, so it doesn't experience a force that way. It just experiences a force, so it's going in a circular path in that plane. Good with that? So one application of this is a particle accelerator. You might have heard of those. Those are things where scientists are trying to figure out the answers to like what makes up things at a really, really small level. So what they do, we have one of these in Chicago. That's our nation's biggest one. It's called the Fermilab. This is over in Europe, CERN. So what they do is they take a proton, we'll say, and they get it going with electromagnets really fast in this loop. This is the warm-up loop. And then they send it out into the bigger one, and then get this thing going close to the speed of light. And then they raise up this sacrificial sample of stuff, and then we take the speed of light moving proton and and just wreckage. And we look at the wreckage. The wreckage is this. Okay. And so what they're trying to do is trying to discover, hey, what's in that after we smashed it all together. And so if you look, these spirals, they're observing this in a magnetic field. This says, hey, this was positively charged. This one was negatively charged. They can figure that and how massive it is and stuff. So that's kind of the evidence that scientists are looking for to see what's under the hood, so to say, or what's the guts to make up a proton or a neutron or stuff like that. I don't think so. Do they do that? I don't know how, but I don't think so. This is like going the other way. This is destructive, not so much constructive. That I'm gonna stop the video. Remember your worksheet.